tau x z, right? Tau x z. Okay. So what's the definition of the n actual force is equal to the integration of the sigma x times the y dz. So this is a area. This is a dz and the dy. Okay. So for the cross is cross section. Divide per 3b. For any element, we have a sigma x, we have a sigma xz, and we have a sigma xy. Sorry, xy. Okay, right? But we do not have loading there, so typically this sigma xy are 0. But the actual force integrate this is a stress and time the area, and you integrate from the whole area, okay? And this dy is okay, is equal to what? The b times the sigma x dz. Okay, okay. That will be the normal force. Actually, this is no actual loading, so the resultant force should be 0. Okay. Then for each local force here is sigma x times the y and times b. Okay. Anyway, the thickness is the unit thickness. If p equal to 1 times the dz. So there's a force at here, and the force times the dz times the moment arm. This is a moment arm. There will be caused a small moment to respect to this axis, right? Then you integrate together from minus half h to h, or whole thickness. So this will cause the moment. Okay, so this is a resultant of the internal stress. Okay, because I mean in the future we draw a beam just like this and we just apply a moment. Okay, if the positive stress and positive coordinate will cause a positive moment, dm. Okay, so this we call the dm. So m is a dm integration, right? Small moment, and we integrate whole cross section, the contribution for all the normal stress. Then we get the total resultant moment. Total resultant moment. Okay, and the shear stress sigma xz. Sigma xz times thickness 1 and times dz. Right? Okay, and we integrate the whole cross section area, whole thickness. Okay, whole thickness. Okay. This is equal to shear force, resulting shear force. Okay, so in the beam theory, what we use here is a resultant force. Okay, resultant force. Okay, yeah. So usually we use a line to represent line, and with EI. So in beam theory, actually in computation, it's just like a line. Okay, bending, shear, things. Right. So this is the main idea from the elasticity or continuum mechanics, from the stress concept, and to integrate together to get resultant forces. Okay, so it's very important. Okay, if in the future, maybe next week, I will show you some theory. If we consider the actual forces, actual stress, like a tendon or something, or PC beam, PC girder, that will also have actual forces. Okay? That will be another theory. Yeah. But this is more the simplest, the linear, we call the Euler beam theory or linear beam theory. Okay. And in this theory, we use a very important assumption is the plane section. plane station remains plane. Okay, after bending. Okay. Okay. Okay, that will cause the theory of deformation. But anyway, so from this, from equilibrium, in the, let's see the equilibrium in the vertical direction. Okay. In z direction, we'll have a force. Okay, minus v. Okay, minus v, and plus q times dx is a force. Okay, it's a force equilibrium. Okay, now the stress equilibrium we call force equilibrium. Plus vertical and plus v plus dv. Okay, is equal to 0, right? So v cancel. So we have dv dx minus q. So this is the first equation we'll obtain related to the internal shear force changing per unit thickness as a change of the q value. Okay. Yeah. And moment equilibrium. Okay. If we take moment equilibrium about point O, okay, we say the force moment about the point O, because this moment is well, yeah, it's not necessary actually. Anyway, okay. This is here. So about point O, and this shear force have no moment arm, so 0. So we have clockwise is moment m, right? And plus this the q dx times the moment arm is half dx. Okay, because this is we have a force q dx equivalent force. Okay, and here, and moment arm is half dx. All right, plus the v plus dv times dx. The dx is the force. Okay, all right, and subtract the moment minus equal to 0. This is equilibrium of moment at point O, right? So you can see m cancel each other, right? And here dx is a high order term, too small, 0. Okay. And also dv and dx high order term drop to 0. Okay, high order term. Hot. Okay. So from here we have v minus dm. V dx minus dm equal to 0. So we have dm dx is equal to shear. So this is the moment diagram. differentiation about the x is a shear diagram. Okay, that's come from. So we have this come two equilibrium equation, right? So they're very, very fundamental. Okay. Then if we combine these two, so this equation 1 and the equation 2. So combine equation 1 and 2. We have dv over dx equal to d dx dm dx, right? And equal to minus q. So we have a dm dx squared equal to minus q. Okay. This is a maybe called third equation. Okay. Combine 1 and 2, we got 3. All right. So we have 3 equations. Yeah. All right. So this is a force equilibrium. Okay. So no matter what kind of material, what kind of a linear force equilibrium is good for any nonlinear. Okay. The force equilibrium. Now let's look like the stress-strain relationship.